thank you very much for making this workshop and having me here. So I will use the time to give a pretty wild mixture of topics. So it's based on joint work with a couple of colleagues, with Ingrid Dobucci, Massimo Fornazier, Karin Schnass, and Hemant. So I will tell by different occasions who were the co-authors at different parts. So essentially I will continue where the question after Albert Cohen lecture ended, namely what is the difference between approximation theory and data analysis. So this is exactly the concept of active learning where you choose actively the points. And my point of view is that there is more settings, but actually they can all learn one from another. So no matter which of the topics you are interested in, the results and the problems of the other guys are still of pretty big interest. So I will then give it on 3 different examples. One is very old and classic, well, not very old, but very famous, which is the L1 minimization. The second one would be rich functions and their connection to neural networks. And the final one would be the recent work almost finished with Hemant on sparse additive models. So in approximation theory, the general point of view, really a very general point of view, is that we have a class of objects of interest, which are typically functions, but it might be also vectors, matrices, operators, or anything else, surfaces, for example. And we would like to approximate them by simpler objects, which then might be polynomials, sparse vectors, low-rank matrices, or whatsoever. And typically, there is only approximation going on, as the name suggests. So we are not able to recover the object completely. We only recover it to some error, which means that we have only limited information about the object. We cannot recover the whole function vector matrix without any error. And well, there is many, I mean, the topic is hundreds years old, so there is a lot of different settings and results. So for example, there is different ways how to measure the error. One of them is the worst case error, where you just insist that every function, every matrix gets approximated to some epsilon error. Or there is like average case setting where only the mean value of the error should be small, and you are ready to accept that for few very specific functions, actually the error might be much larger than the average. So the central topic of this workshop, as it's approximation of high-dimensional or multivariate functions, is then the functions of interest depend on many variables, Rd, with d pretty large. The question is how large is large, and the most natural setting is that we want to approximate f only by knowing few of the function values. Of course, as such, the setting is very, very general, and there is a huge amount of questions which are on the table. So I collected some of them here. So we have to assume something about the f. So if the f would be general integrable function, that function values are not indeed defined at all. So there must be some assumptions on f. Typically, that would be smoothness, for example. So in which way to measure the error, how to choose the sampling points, how to design the algorithms which take the information and combine it to produce some f tilde, which is a candidate for f. I'm also pretty much interested in optimality results, which is like the lower bounds, telling you that no algorithm can perform better than something which you already have, such that you know that the algorithm on the table is maybe up to constants, which, as Albert Cohen put it, land below the rug, is unimprovable. And the very crucial thing in multivariate approximation is, of course, the dependence on D. So in data analysis, the point of view seems to be very, very different. So in the beginning, you don't have a function at all. You just have a data, which actually nowadays might mean essentially anything. It might be very heterogeneous. It might have different components. It might be a mixture of real numbers, vectors, angles, and all the different stuffs. And essentially, you would like in one of the settings, so this is not even the most general setting, you would like to learn the dependence of the output on the input in such a way that if you get a new input, then you can get the output, you predict the output with some reasonable speed and with some reasonable accuracy. So because, I mean, in this part, sometimes at least, you don't prove any theorems, you just want to see the results. You learn from part of the data set and you test on the other part, and in this way you test if your procedure is okay or not. So in mathematics, we make the proof, and if the proof is correct, we are happy. If not, well, then we try to fix it. Here you just test on 1/2 or 90% of the data, and you test on the rest, and if the errors are okay, then that is like the certificate of the right method. Well, there is also theory, of course, around a lot of, and the most standard assumption is that you assume that the data was somehow drawn from independent, like independent samples of some distribution. This seems to be reasonable, but of course, if you think about in detail, then, well, it's again a bit of question. So if, for example, the input data would be blood tests of some patients which came to the hospital, and the dependence is if they are sick or not, then of course, this people coming to the hospital in one small city, the pretty big preselection of who you actually measure. And if you start to measure someone else in some bigger city or in some other continent, the distribution might change completely. Finally, also the independence is maybe not really clear here. I mean, the people entered independently, but that doesn't mean that mathematically it's independent samples. So altogether, I mean, this is also an assumption, and I will come to that later, that anytime you have an assumption, you have a situation where the assumption is not really fulfilled. So there is hundreds, thousands, or even more methods of how to deal with data, and two most simple ones are least squares, where you just, which we've seen now for quite a long part of the Albert Cohen's talk. And I will later on come to L1 minimization, where the usual, least square method is perturbed or has an additional regularization term, which is just the L1 norm of this vector omega. Another method would be, say, PCA, which is actually, well, doing the same, only now you want to have a subspace. You don't have any outputs. You want to have a subspace which somehow fits the data. And again, it's a very classical method with implementations available and so on. So in general, approximation theory and data analysis, they both try to learn, and they all make assumptions. And two quotes which I like very much when it comes to the relation of the theory and practice come from Goethe, who says that actually all the theory is gray, but the life is, always green. And the last, and the second one actually connects very nicely London and Prague, because it's from Sherlock Holmes in Scandal in Bohemia, where it says that you should always first look on the data before you make the theories, in such a way that you don't make the theories specific to the data. So approximation theory has assumptions, like the class of the functions of interest. So you need to assume that the function is smooth, but you don't know the function yet. You want to learn it. How do you know that it's smooth? I mean, it's obviously turning in a cycle. Well, there is few situations where you really might know. So we know that the solution of a PDE with some right-hand side is really smooth somehow. We can prove that. So if we know that the right-hand side is continuous, then we know something about the solution. But that is like one very specific example. And in approximation theory, we typically assume that the data points you can choose as you wish. You have to say how you do that. If you do it, deterministically, or you sample with respect to some measure and which measure and so on at random. But at the end, you assume that essentially all the points of the domain of interest are feasible. Well, in practice, this is not always the case. So if the xi's, for example, which I had here, if they really are some blood tests of someone, that for some combination of the data on the blood test, there is no person which would have this specific data measured in his blood test. So because, I mean, all the blood tests of humans, they are actually quite similar to each other. So although the domain here, which theoretically x1 up to xn can be from, might be pretty large, the feasible samples are not scattered all around. And you cannot somehow design a people, so you have to live with the guys who just came to the hospital somehow. So the active choice of points might be really an issue. Well, although data analysis typically looks like a very applied science, when it comes to theoretical results, there are also assumptions. And again, it's not really that clear if these assumptions are always fulfilled. So, for example, the independence is not always really secured. So if someone from a family would come to the doctor, there is a pretty big danger that his relatives would come on the next day, which doesn't make it independent. I mean, it's a very, very specific choice of the samples then. The underlying probability, which is unknown, it also has to satisfy some, assumptions, at least in most of the theorems. And because it's unknown, it's again pretty difficult to verify if it really satisfies or not. So, and finally, the success measured by the leave-out data, so there is no proof, there is a good performance on data on the table, which is important, surely, but still, it means that if someone gives you other bunch of data from the same area measured just once more on a different set of patients or whatsoever, it might turn out that by at least some small percent, you perform better or worse just because you had another data on the table. So if you have 5 different methods which do, perform very similarly, at one point you might say one is better because it's slightly better than the others. If the data was collected 1 week later, you would have the opinion actually the other one is better because, well, the small margin between them just changes. So it's indeed a pretty tricky business how to get some intuition about what is reasonable and what not. One thing which I would like to essentially repeat from what Albert Cohen said in his talk is that nowadays you can actually sample much more actively than before. So there is a lot of people in the world running with a full hard drive of data and trying to learn something out of that. But there is also people who, before they collect the data, think about how to collect that. And if they have the possibility to, for example, run a PDE to get the data, then actually they might design the calculation by putting the right initial condition in there. So in one application which I met a few years ago in material science, that was exactly what actually happened. So that is a department of physics in Berlin, where I was some years ago. Well, I was not in that department, but I was in Berlin. And I met the guys, and to my own surprise, they do not have any lab anymore. I mean, they do not see the materials which they write the papers about. The materials maybe never, existed. They just threw out all the, equipment they had before, and they bought a supercomputer into the same space. So they all, calculate the material properties just from Schrödinger equation and the description of the material. So they can actually cook up virtually any possible material, calculate its properties, and only when they see that these properties are of interest, they would really start to think about how to synthesize the material. Is it expensive or not? And maybe even to remeasure if the calculation was correct. But actually, because Schrödinger equation is a very good tool since 100 years, it's known that their PDE solvers are exact up to like 4 or 5 places behind the comma. So actually, they do not really care so much about remeasuring what they calculated. They did that 20 years ago. And they found out that this method is so well tuned that this is nearly exact. So there is virtually no noise in the data, actually. So, and with that, the situation is quite simple. So they would like to have new materials with some new fancy properties. So the property is the function f, and the way how you describe the material, so which atom sits where, is the, well, parameter p, which actually might be quite large, because if you think about some more complex materials, there might be different crystal where on different places you exchange something for something. So this p can easily live in dimension of 50 or 100 or more. So there might be some angles, some geometry, some composition, and all that together combine in the p. So for 1p, they are actually able to calculate. The supercomputer is there. The method called LDA is very famous, and they can really do it, but it takes few days. So they can do that, but it really is no matter of minutes. It really requires pretty much work. So it's a really expensive simulation. So they can do that for, say, 20, 50, 80 materials if there is a really good reason to do that, but they cannot do that for 1,000. That would require, collaboration through the whole Europe. So they have a nearly noise-free sampling possible here. They can choose the piece, at least to some extent, in a pretty big area. They can actually calculate properties of materials which do not, exist at all. The LDA calculation can deal with things like non-integer number of protons, which, don't ask me what it is, but they believe it makes sense. And finally, one thing which I was very keen about, but unfortunately I didn't follow at all, they have a very interesting trade-off. If they are fine with pretty noisy outcome, with only pretty rough calculation of the property on the table, they can do it much more quickly. So you can have a lot of noisy samples or few of actually noiseless samples. And obviously, this is a very interesting trade-off where you should be able to say what is actually better or how to combine these two things. So is it better to have very few but very noiseless samples, or is it better to have a large number but of very noisy samples? I mean, it's not really clear, or if is some mixture actually better, better. So I will not speak about this application, but if you would be interested, it's a really interesting business, and they follow this project and employ now like 25 postdocs just doing machine learning for material science data. So my point of view in this talk is that actually approximation theory and data analysis study the same thing from different points of view, and they can actually enrich one the other if combined correctly. So I will try to give 3 examples. One is very classical, and it's L1 minimization, which actually appeared maybe even before, but got really famous through the paper of Tibshirani in '96. And it's what I already mentioned, namely that to the least square minimization problem, which we've seen in extensive treatment in Albert Cohen's talk, you give L1 penalization term, and the lambda, which is somewhere there, gives you the weight between the quality of the fit and the number of non-zero components of this omega. So as such, the Tibshirani paper was an important breakthrough. It was a sort of a feature selection operator. So it was the advent of interesting new methods for dealing with high-dimensional data and discovering low-dimensional structures in there. But of course, it leaves a number of questions open. I mean, the computer always runs, and the computer always gives you something at the very end. But on the other hand, me as I am, I would like to know in advance, before I push the button, if it was actually a reasonable thing to do. If there is a reasonable hope that the method used on the data on the table has a chance of giving something reasonable. So, for example, as such, if I only write this line down before it comes to any analysis, it's difficult to say how many data points you need to learn what you actually wanted to learn. So especially how it scales with the number of degrees of freedom or with the dimension behind. And the theory was, well, an L1 minimization from the point of view of approximation theory is the famous area of compressensing. So if omega or, well, W is sparse, you might want to consider linear functions of this kind. So your class of functions, which we like to have in approximation theory, will be linear functions which are generated by sparse vectors. And we are allowed to design a method to design sampling points, namely these xj's, so to measure these scalar products at pre-selected xj's. And we are allowed to design a recovery algorithm which from these data, from these measurements, from these scalar products, will get as close to the W as possible. And the answer is it's the L1 minimization. But of course, it's only one of the candidates. After the enormous work on compressensing in the last decade, there is tens of different algorithms on the table, but L1 was like the most prominent in the beginning. And even more important, it tells you about how to choose the points, how many you need, and so on. So it answers actually a few of the questions which I had here at the end of this slide. So especially it tells you that if you take xj's at random, which seemed to be a bit unusual for data analysis first, and taking only s times log d of them, so if W has only s non-zero components, then it scales only logarithmically with d. So we've seen in Albert Cohen's talk the curse of dimensionality, where dependence on dimension is very bad. And actually, I believe that a good portion of the success of compressensing can be explained by this log d, because it scales so well with the dimension. So nowadays, if the dimension goes to billions, seems like trouble, but you take the log of that and you get it back to normal somehow. So this log d is really an important feature here. So there is, I think something like 20,000 papers about compressensing. So if I summarize all of them into 3 lines, which is pretty ambitious anyway, then it says that if you follow the scheme I had on the last slide, then taking independent Gaussian measurements gives you what you wanted with L1 minimization and actually with equality. So this is another surprising thing. There is no approximation which one would naturally expect in approximation theory. There is actually exact identification. So now my point of view is that approximation theory and data analysis can really enrich each other. So what can we learn from the approximation theory of L1 minimization for the data analysis? So in data analysis, you are not really allowed to design independent Gaussian random variables to measure something, but some of their properties, like incoherence, for example, might be pretty general techniques, at least intuitively. So there is even theorem about that, but still. So I would suggest the doctor, if going for some sparse classifier of some tumor, that if possible, choose the patients not from one small city, but choose them across the continents, across the cities, in such a way that they really have different features inside and they really represent all the possibilities which can happen. So do not measure one family altogether day after day, but try to measure worldwide and try to collect mostly uncorrelated data altogether. And finally, it tells you that if you succeed in that and your sampling, your measurements follows as much as possible this incoherence of Gaussians, then actually the number of patients to measure can be described by a formula with S log D. We actually have here pretty good track of the constants, and they are like 4 or 6. So it's actually not that bad. So it can really give you a pretty good estimate on how many measurements to include in a clinical test and how to design it. Of course, you get quickly on the boundaries of what is possible, but at least it gives you a bit of intuition. So now to the other two applications. So that would be rich functions and sparse additive models. So rich functions are simply functions where f of x takes this shape of univariate function of a scalar product of unknown vector a with the variable x. So obviously they are constant as soon as a of x, a scalar product with x is constant. So they are constant along these hyperplanes. And you can easily generalize that if you say A is not a vector, it is a matrix with more than one line, then you get what we call K-rich functions. They appear in mathematics in many different places as simple objects, simple building blocks for more difficult constructions. So we find them in Fourier and Radon transform. We find them under the name of plane waves. And actually, they were used in Richlets, curvelets as building blocks for functions with singularities along lines. They actually appeared in approximation theory at the end of 80s, beginning of 90s. And already in that time, it was in connection with neural networks, which you see from the title of the last paper, which is all about neural networks. So taking functions like that, which is a simple, modification of what I had, Pincus, Lin, and others were able to prove that you can approximate a lot of different functions from the span of functions like this, at least if the number of parameters goes to infinity. Well, it's like bringing Ols to Athens to talk about neural networks here. But let me sketch at least few notation here. So they appeared in 40s already quite a long time ago, and they were popular at one point, but around 80s they cleared the space for like support vector machines and L1 minimization and other simple minimization algorithms. But it actually re-arrived like 5 or 10 years ago with a pretty big success in, well, beating humans in chess and Go and other important stuff. So what is a neural network? Well, it is a combination of artificial neurons, and neurons have some inputs which they combine with some weights, and they output the scalar product. And then there is something which is called activation function, which is essentially some step function a bit smoothed. So there is a number of different candidates of how to smooth sine function. And typically the sigma is actually prescribed. So typically in the neural network, the sigma is not really optimized for. It's taken as a parameter which is fixed. So you see already that actually artificial neuron is a sort of rich function with indeed unknown parameter of weights of w's. The only difference to what I had before is that sigma is actually known or assumed to be known. And in a neural network, then you combine all these into layers which shift their inputs to their outputs, which become inputs for the new layer, and so on and so on. And the advent of neural networks recently was just given by, well, computational powers which were able to really learn, to really optimize for these Ws over a very huge space, where the deep learning means that you don't have 1 or 2 or 3 layers, it can go to hundreds. So in the 70s, this was just computationally infeasible, and that's why at one point the field was essentially abandoned. But nowadays, with special GPUs and so on, this task can be really, really done. So as such, because optimize over these Ws is non-convex, there is mathematically a number of disasters which actually people fight actively all over the world nowadays. So we will see a few of them in my talk in a few minutes. So first, if you have only one rich function, so a very simple neuron, so to say, it has only one input and one output. So it's really, it has D inputs but only one output. It's really like one rich function here. You see how to recover it very quickly, because if you differentiate the function, then actually you get the unknown vector A as the outcome. So the gradient of f would be a multiple of the unknown A. So if you are able to calculate the gradient of such a rich function, then you actually get your A very quickly. Obviously, there is two troubles with that. First, if this quantity, this g prime of A times x is 0, then you get a multiple, but very small one, or actually a 0 multiple from which you cannot learn anything. And the second thing is, well, you need to use some numerical scheme to approximate derivatives, which is also numerically difficult, especially if your sampling is noisy. So there is these two issues which are somehow in there and like difficult to fight with. So in a paper which appeared again before the new hype of neural networks, Baumann and Pincus identified sum of rich functions, so essentially like one layer of a neural network. But their scheme was numerically, well, it was, theoretical paper, so theoretically there is nothing bad about that. But they use very high order derivatives. So if the m is the order of the sum, they used 2 to the m minus 1 derivatives, which numerically, if m is 3, then you see what's going on here. So they were able to put together a few equations from which they could solve and identify the components, but numerically this seems to be pretty unfeasible. So in another paper, but already, you notice the nearly 15 years gap between these two papers, and especially the compress sensing area which happened in between. Albert Cohen, Ingrid Dobucci, Ron Devor, Kerkicharian, and Picard, they actually followed another line of research. So it was restricted to k equal to 1. F was defined on the unit cube of Rd, with G to be smooth a bit, and with A to be essentially sparse. So this condition that LQ norm with Q smaller than 1, this is the typical compress sensing compressibility condition. So already this bold line, the fifth one, tells you that it essentially goes into compress sensing direction. And one restriction which was in there as well was that A is positive. So all the components of this unknown rich profile of this A were assumed to be positive. And with that, they could cook up an algorithm to uniformly approximate f up to this error with this log d term coming from compress sensing and being very convenient if dimension grows huge, with only few sampling points needed. So the idea is sketched here. So you sample along the diagonal, and because you know that the A is positive, you know that actually scalar product of A with x is growing along the diagonal. So you actually sample the unknown function g first on a grid, although you don't know the A, you know that it's actually monotonically growing, and then you find a point somewhere on the diagonal where the step, where the difference in these samples was the largest. There you differentiate, and then you get compressing setup and equations which you solve by the algorithms there. Okay, we followed with Karen Schnass and Massimo Fornazier this line essentially very quickly after, and with the same compressibility condition, but with no positivity on A, we essentially updated the setup in some way. So we cooked up also compressing equations from this setup, namely doing first order differences of the function f. So we essentially go back to the first line where I said differentiating f gives you the rich direction. So differentiating f in random directions gives you measurements of A with respect to random vectors. And from that, you can apply compressing back again, and you get what you wanted. So the final theorem was actually quite similar to what we had before, with some log D term again inside. And well, the setup of an L1 minimization in the middle. There is a number of other different settings, and actually there would be too many papers to mention here. So setting of active coordinates, which is essentially what you see here on this line in the middle, is that there is a huge number of parameters, but not all of them actually play a role at all. So only few of them are of some importance, but those which are important, they might be combined in a nonlinear way. This was followed by Hemant and Wolfgang Zevher around the same time, shortly after as well, with low-rank matrix recovery. So when it comes to sum of rich functions, we actually come closer to the concept of neural networks. And in the work which took us several years, we faced different number of, large number of different problems. So on many occasions, half of the way, we were thinking about just dropping the topic until we noticed that actually so many people are interested in the same troubles nowadays, because they started to learn to study or to analyze neural networks, that we are essentially finishing the paper right now. So the idea is that first we reduce the dimensionality. So there is a short sum from 1 to k of such rich functions, but the dimension of A is assumed to be huge, in order of, say, hundreds. So if we could reduce from D to K, that would definitely make the things easier. And, well, if you accept the troubles of numerical differentiation, it is indeed possible. So because the gradient is a linear combination of these AJs. So if you do the gradient on several different places, you get several different combinations of AJs. And with a number of places to test, you essentially recover the span of all these A's. And you can reduce from your RD to this k-dimensional subspace spanned by this A1 up to AK. Once you do that, well, still it's not exactly what you wanted. You want to have A1 up to AK. So now when the dimension reduced from D to K, we go for second order derivatives. So that would be deadly if the D would be, say, in the order of hundreds or thousands. But if you reduce to K equal to 15, it starts to be feasible again. And if you do the second order derivatives, you get a linear combination of rank 1 matrices, namely the AJ tensored with AJ themselves. So repeating the technique of calculating this matrix, this Hessian matrix on different places, you get a span of these rank 1 matrices as a subspace of the set of matrices. Unfortunately, again, as usually, you don't get it exactly, you get only some approximation of it. So essentially, it boils down to the problem to finding matrices with the lowest rank in such a space L, or better said, L tilde. Because if we find, I mean, the only rank 1 matrices in this subspace are A1 times A1. If we have such a matrix, we can, maybe up to the sign, find the A1 itself. So that would solve the problem. So essentially, we would like to find the matrices of minimal rank or minimal numerical rank if it's only the approximation. So we propose an algorithm which goes like that, which is non-convex, and I will come to that. So we maximize the operator norm over the Frobenius unit ball on this subspace. So this is clearly a non-convex procedure, and actually it must be, because if you have a space like this, then actually it has at least k matrices which have rank 1. So if your algorithm has a chance to land in one of them, by symmetry, it must have a chance to land in any of the others. So it must be non-convex. So that's it. And under some assumptions, we were able to analyze this algorithm, but, well, the results are too technical to put them here, where essentially we say that under some nearly orthogonality assumptions on AJs, anytime you land up in any local maximizer of this algorithm, it must be very close to such an AJ times AJ matrix. And, well, to formalize all that took a couple of years to us and pretty much headaches. So now to the last section, which is the recent work with Heman on sparse additive models. So one way, I mean, this is a bit different than the rich functions and the neural networks concept, because there is no rich direction. There is no vector to learn. We only assume that few of the coordinates are important, and those which are important independently, at least in this very simple setting first. So the function f is a sum of univariate functions, where each of these univariate functions depends on one of the xj which you already have. So you don't need to rotate anything, because the x's are already such that the function can be described like that. And the name sparse corresponds to the fact that we assume that only few of them are actually important. So the cardinality of the sum is actually much smaller than the full dimension of the problem. You can easily generalize the model to higher order, like bilinear functions here, where to what you already have on the table, you add some bilinear terms, which again is sparse, so not all possible pairs actually appear. And it's no trouble to at least formally write it down, even for general R0 order of this additive model, where you go up to, well, finite R0 here. And we assume all the components to have actually much smaller dimensionality than what the possible maximum would be. So to ensure uniqueness, which is of course convenient to measure the errors, we worked what is called anchored ANOVA decomposition. This is essentially quickly described here by these 3 lines. Namely, we assume that, so first, this uniqueness is really not in there, because if to such a function f, if to each phi j you add or subtract a constant which sum up to 0, then you get another decomposition of f where you change the phi j's in an immaterial way, but you destroy the uniqueness of that. So to make it correct, one can show that such a decomposition is already unique. Namely, you first take the value at 0, and after you subtract fx minus f0, then actually there is no need to choose these components, these phi j's or fi's here, to have a non-zero value at 0, because there they only need to sum up to 0, so we fix them to be all equal to 0 there. With such, you get a function which is already good on the coordinate axis. So for the bilinear terms, you can assume that anytime xi or xj is 0, the function is 0, and so on. Okay, So just to give you few hints about what we did and which technique we combined. So in the univariate case, we assume that the function value at 0, which is called mu here, was pulled out, and that the phi's are smooth and they are identifiable. We are interested in exact recovery of these S1, of this, well, important coordinates involved. So there must be some point in which they are large. So we will have, until the end of my talk, smoothness and identifiability assumption. And what we do is the following. So we would like to sample each of the phi j on a grid. But we would like to do it at once, not to do a grid for every of the functions independently, because that would be too costly. And with such a vector on the diagonal, we can actually do that. So we do a grid on the diagonal, and we generate beta to be random signs from -1, +1. And these 2 points, x plus and x minus, are then done in such a way that x plus is equal to the original x if the beta was +1, and x minus is equal to x if beta was -1. And if you then subtract f in x plus minus f in x minus, then because of this anchored ANOVA effect, anytime there is a 0 here, this term actually cancels out completely. You get a formula like that, which resembles very much compressensing. So the main advantage of all that, I believe, is that there is no finite order differences involved. So there is no plus minus epsilon, there is no divide by small h and amplify the noise. There is just 2 points which might lie actually very far from each other, because once you keep half of the x's and on the other case you keep the other halves, so they are not really connected one with each other. And there is no division by something small, so no amplification of noise. And you get the compressensing scheme of unknown sparse vector measured with a vector of random signs, well, with a random Bernoulli vector, which of course is good for compressensing and which is very well known. So the algorithm is then for each point on this diagonal, you generate signs, you do the compressensing scheme, you recover the approximate solution, and because you know that the function phi j was large, at least at one point, at some point on the diagonal, your recovered z tilde must be large as well, meaning that if you go through all the diagonal and collect all the indices where the compressensing solution was large, at the end of the day, you'll end up with exactly S1 equal to S1 tilde. So you really recover exactly the active coordinates. For the bilinear case or the bivariate case, the setting is quite similar. The assumptions are nearly the same, so smoothness and identifiability. But the trouble is the diagonal is not exactly what you need here anymore. So you need to sample each of the phi j1, j2 on a 2-dimensional grid. And again, you would like to do it at once, not to sample for each of them extra. So instead of 2 points, you produce 4 points. So that's the exponential dependence in R0 coming out. So we take a decomposition of indices 1 to d into A1 and A2, disjoint decomposition of the index set. And we take not points on the diagonal, but on the 2-dimensional grid. So we take L1 and L2 instead only of 1L. And from A1, we put it L1 over M. From A2, we put it L2 over M. And then we cook 4 points depending on the signs and on the A's, which has to be checked, and it's, a bit technical first, that they satisfy a very nice analogy of the sampling scheme before. If you combine these 4 sampling points, which again lie very far from each other, there is no division by small h, then you get measurements like that. So there is again a scalar product of some randomness with the things you are interested in. But there is one pretty important change, namely the randomness is not independent. So if there would be beta J1, J2, and all the betas would be independent, that would be compress sensing in its most favorite form. But here, there is much less randomness, which is very well known to be pretty bad for compress sensing. The less randomness you have, the worse the recovery results typically are. So we get billionaire compress sensing measurements of this sparse vector, but not with random Bernoulli vector, but with a billionaire random Bernoulli vector, or rank 1 random Bernoulli matrix. Fortunately, there is a result about that, which is called Hansen-Wright inequality, which is doing exactly the same, although in a more complicated way than in the usual compress sensing business, which tells you that it's indeed possible and doable. So in this billionaire case, for all the possible splittings of A1 and A2, such that they separate each pair into two different sets, which is a thing called hash families in theoretical computer science, we can proceed in a very similar way as before. So the important thing is that the size of such a hash family is again only logarithmical in D, which, well, there is a easy random proof of that. There is more sophisticated non-random proof or deterministic proof of that. Well, for the multivariate case, I only would say that it was possible to somehow continue that. So instead of R0, 1, or 2, you would have R0 general. The hash families would now split 1 to D not into 2 parts, but R0 parts. The sampling scheme doesn't use 2 to the 2, but 2 to the R0 sampling points, combined with some plus minus signs deterministically designed, as it was here. So there was nothing random about the signs which you see around the Fs. And with that, we could get recovery guarantees, but because of the lack of Hansen-Wright inequality, they unfortunately became quadratic in SR0, but still logarithmic in D. So as a summary, there is a lot of work in different of these settings. So especially for high-dimensional approximation theory, it seems that nonlinear quantities and nonlinear classes are very important, that convex classes somehow cannot really do the job in high dimensions. The geometrical properties of a set of neural networks of functions which can be designed or interpreted as a neural network seems to be very challenging for the next future. And with that, I would like to thank you for your attention.